Hello everybody. Today we are going to learn about surfactants. It is also known as surface active agents. This topic is related with physical chemistry and it is a part of surface chemistry. Here you can see the overview of my presentation. Flow of my presentation is related with first definition of surfactants, second one is classification of surfactants, third one is properties of surfactants, and the last one applications of these surface active agents. First, we will talk about the definition of surface active agents, then the classification of surfactants, some basic properties of surfactants, and the applicable or uses of these surfactants. Before we start, I want to say some basic terminology of this topic. So, here you can see first hydrophilic. It means a liquid or a surface that has a high affinity to water. In other words, affection or attraction towards the water molecule. You can easily say a liquid or surface that has a high affinity to water. In other words, affection towards the water molecule. Second word is hydrophobic. That means a liquid or a surface that has very low affection to water molecule. Third one is lipophilic. It means a liquid or surface that has a high affinity to oil. It means high affection towards the oil. Fourth one is lipophobic. It means a liquid or a surface that has a very low affinity to oil, very low affection towards the oil. It's a basic terminology of surface chemistry. One is hydrophilic, that means high affinity to water molecule. Hydrophobic, that has very low affinity to water. Lipophilic, that has a high affinity towards the oil. Lipophobic, that means a very low affinity to oil. Understood here? Okay. So let's start from the beginning. Surface active agents. What is surfactants or surfact active agents? Surfactants are compounds that lower the surface tension. It means or interfacial tension. Surfactants are compounds that lower the surface tension between two liquids, between a gas and a liquid, or between a liquid and a solid. It is very easy to say. It is very easy way we can say a molecule that contains a polar portion and a non-polar portion is called surfactants. In very easy way, what I can say? A molecule that contains a polar portion and a non-polar portion is called surfactants. Molecules and ions that are absorbed at the interface is termed as surfactants. In other words, molecules and ions that are absorbed at the interface is termed as surfactants. Surfactants are usually organic compounds that are amphiphilic, meaning they contain both hydrophobic group and hydrophilic groups. Therefore, a surfactant contains both a water insoluble or oil soluble compound and water soluble component. Surfactants will diffuse in water and absorb interfaces between air and water or at the interfaces between oil and water in the case where water is mixed with oil. The water insoluble hydrophobic group may extend out of the bulk water phase into the air or into the oil phase, while the water soluble head group remains in the water phase. In short, we can say surfactants have two distinct regions in their chemical structure. How many distinct regions? Surfactants have two distinct regions in their chemical structure. One of which is water liking. Water liking means hydrophilic group, and the other of water hating. It means hydrophobic. Surfactants have two distinct regions. One is Water liking, it means hydrophilic, and other one is water hating, it means hydrophobic. These molecules are referred to as amphiphilic or amphipathic molecules, or simply as surfactants. These molecules are referred to as amphiphilic and amphipathic molecules, or simply you can say the surfactants. A surfactant can interact with both polar and non-polar molecules. A molecule that contains a polar portion as well as non-polar portion. It is known as surface active agents or surfactants. A surfactant increases the solubility of the insoluble substance. What I can say? A surfactant increases the solubility of the other insoluble substances. In water, surfactants molecules tend to cluster into a spherical geometry. Non-polar ends on the inside of the sphere, polar ends on the outside. These clusters are called micelles. In water, surfactants molecules tend to make cluster into a spherical geometry. Non-polar ends on the inside of the sphere and polar ends on the outside of the sphere. These clusters are known as micelles. Surfactants are known to play a vital role in many processes of interest in both fundamental and applied sciences. One important property of surfactant is the formulation of colloidal sized clusters in solutions known as micelles. Earlier I can say in water, surfactant molecule tend to make cluster into a spherical geometry. Non-polar ends on the inside of the sphere, polar ends on the outside of the sphere. These clusters are called micelles. But in other way, one important property of surfactant is the formation of colloidal sized cluster in solutions, and it is also known as micelles. Micelles have particular significance in pharmacy because their ability to increase the solubility of springly soluble substances in water. It is very useful for the pharmacy. Micelles have particular significance in pharmacy. Why? Because their ability to increase the solubility of springly soluble substances in water. Surfactants are widely used in molecular biology, in formation of new and modifying existing medical preparations, in the production of chemical preparations aimed for the domestic use, etc. This is the micelles applicable in the pharmacy as well as molecular biology and also in medical and chemical preparations. So, surfactants are amphiphilic molecules composed of a hydrophilic or a polar moiety known as head and a hydrophobic or non-polar moiety known as a tail. Hydrophilic means water liking. It is a polar moiety and it is known as a head portion, and hydrophilic means water hating properties or a non-polar moiety and it is known as a tail. The nature and the number of polar and non-polar groups, hydrophilic, lipophilic or somewhere in between. The nature and the number of polar and non-polar groups, hydrophilic, lipophilic or somewhere in between. For an example, alcohols, amines, acid changes from hydrophilic to lipophilic as carbon atoms increasing in their alkyl chain. For an example, alcohols, amines and acids changes from hydrophilic nature to lipophilic. How? Carbon atoms increasing in their alkyl chain. Here you can see the structure of surfactants. The upper portion of figure shows the hydrophilic head, means affection towards the water molecule or water liking moiety. It is a polar moiety and known as a head. But in figure, lower portion shows the water hating part. It means hating towards the water molecule. Okay, this is the hydrophobic tail, and the water liking or water affection towards the water molecule, it is head and it is known as a hydrophilic head, and about tail, it is hydrophobic. In short, All surfactants are characterized by having two regions in their molecular structure. In short, all surfactants are characterized by having two regions in their molecular structure. One is hydrophobic group, second one is hydrophilic group. In hydrophobic group, such as a hydrocarbon chain that has no affinity for aqueous solution, non-polar portion. Hydrophobic group means such as a hydrocarbon chain that has no affinity for aqueous solvent. It is non-polar portion and it is known as a hydrophobic tail. But a hydrophilic group that has an affinity, attraction for the water molecule. It is polar portion and it is known as a hydrophilic head. Now let's talk about classification of surfactants. So depend on the molecular composition and the nature of dissociation of their polar head groups, the surfactants are classified in four classes. One, anionic surfactants, second one is cationic surfactant, third one is non-ionic surfactant, fourth one is amphoteric or zwitterionic surfactants. Now from anionic surfactants, anionic surfactants have a negative charge on their hydrophilic end. Anionic surfactants have a negative charge on their hydrophilic end. The negative charge helps the surfactant molecules lift and suspend soils in micelles because they are able to attack a broad range of soils. Anionic surfactants are used frequently in soaps and detergents. Anionic surfactants create a lot of foam when mixed, while anionic surfactants are excellent for lifting and suspending particulate soils. They are not as good at emulsifying oily soils. So, anionic surfactants have a negative charge on their hydrophilic end. The negative charge helps the surfactant molecules lift and suspend soils in micelles. So, it is useful for soaps and detergent. These are also further categorized based on permanent anion, permanent negative charge or pH dependent anions. They are categorized as sulfates, sulfonates, phosphates, carboxylates. For an example, sulfates. Some alkyl sulfates, some alkyl ether sulfates are related with the sulfates. About sulfonates, sulfonate fluorosurfactants, alkyl benzene sulfonates, it is a part of anionic surfactants. Third one is phosphates, alkyl aryl ether phosphate, alkyl ether phosphate, it is related with the phosphate anionic surfactant. And the relation of carboxylates, for an example, alkyl carboxylate, carboxylate fluorosurfactant, it is carboxylate anionic surfactant. More than 60% of industrial surfactants are related with the anionic surfactants only, and this is categorized by four types: sulfate, sulfonates, phosphate, carboxylate. More than 60% of industrial surfactants are based on anionic surfactant, based on permanent negative charge. Okay. Now we will talk about cationic surfactant. Cationic surfactants have a positive charge on their hydrophilic end. The positive charge makes them useful in anti-static products like fabric softeners. Cationic surfactants can also serve as antimicrobial agents, so they are often used in disinfects. Cationic surfactants have a positive charge on their hydrophilic end. The positive charge make them useful for anti-static product. For an example, fabric softeners. Cationic surfactant can also serve as a antimicrobial agents. So it is useful for the disinfectants. Cationic surfactants cannot be used with anionic surfactant. It is very much useful point. Cationic surfactants cannot be used with anionic surfactant. If Positively charged cationic surfactants are mixed with negatively charged anionic surfactants. They will fall out of solution and no longer be effective. Why we cannot use anionic surfactant with cationic surfactant? Because if positively charged surfactant are mixed with negatively charged surfactant, what will happen? They will fall out of solution and no longer be effective. Cationic and non-ionic surfactants, however, are compatible. For an example, some common cationic surfactants include alkyl ammonium chloride. Now, you can see based on pH dependent primary, secondary or tertiary amines. For an example, primary amine becomes positively charged at pH less than 10. Secondary amines becomes charged at pH less than 4. Some examples related with the cationic surfactant you can see here: cetyl pyridinium chloride, CPC, cetyl pyridinium chloride; polyethoxylated taloamine, POEA, polyethoxylated taloamine. Some other are also useful as a cationic surfactant. Now we will talk about amphoteric or zwitter ionic surfactants. Amphoteric surfactants have a dual charge on their hydrophilic, both positive as well as negative. Amphoteric surfactants have a dual charge on their hydrophilic end, both positive as well as negative. The dual charges cancel each other out, creating a net charge of 0, referred to as a zwitterionic. How can we say zwitterionic? So, amphoteric surfactants have a dual charge on their hydrophilic end, both positive and negative. So, the dual charges cancel each other out, creating a net charge of 0. That's why it is referred to as a zwitterionic. The pH of any given solution will determine how the amphoteric surfactants react. In acidic solution, the amphoteric surfactants become positively charged and behave similarly to cationic surfactants. In alkaline solution, they develop a negative charge similarly to anionic surfactants. So, amphoteric surfactants are often used in personal care products such as shampoos and cosmetics. Amphoteric surfactants are characterized by the fact that these surfactants can carry a positive charge on a cationic site and a negative charge on an anionic site. In simple way, positive charge on a cationic site and negative charge on an anionic site. The use of amphoteric terminology is still restrictive. The charge of the molecule must change with pH. Earlier I can say, I already say in acidic solution the amphoteric surfactant become positively charged and behave similarly to cationic surfactant, and in alkaline solution it means in basic solutions they develop a negative charge similar to anionic surfactant. So the charge of the molecule must change with pH, showing a zwitterionic form at an intermediate pH. Some examples of amphoterics are amino acids, amino acids, betanes, lecithin. It is related with the amphoteric or zwitterionic. Now, last one is non-ionic surfactant. Non-ionic surfactants are neutral. They do not have charge on their hydrophilic end. Non-ionic surfactants are neutral. They do not have any charge on their hydrophilic, and non-ionic surfactants are very good emulsifying oils and are better than anionic surfactant at removing organic soils. They doesn't include any charged head. These are categorized as: one is fatty alcohols, polyoxyethylene glycol, polyoxypropylene glycol, glucosides, polyoxyethylene glycol, octyl phenol ethers, sorbitane alkyl esters. These are related with the non-ionic surfactants. Now, applications of surfactants. Surfactants are very much useful in some kind of uses. Detergents, fabric softeners, emulsifying agents in emulsions, laxatives, anti-fogging agents, as an adhesive, as in inks, some anti-fogs compound, suspending agents in suspensions. So there are many uses of these surfactants. Thank you.